Welcome to Maths with EJD. In this video, I'll be talking about eigenvalues and eigenvectors in PageRank algorithm used by Google. Previously, we had considered some applications of eigenvalues and eigenvectors in principal component analysis, which is in data science, in sound, in vibration analysis, in mechanical engineering, in um, quantum mechanics. Yes, we've seen all of that too. So here now we're looking at eigenvalues and eigenvectors and PageRank algorithm. So first of all, um, the PageRank algorithm developed by Google founders Larry Page, and Sergey Brin. So the Google founders. So the algorithm ranks web pages based on their importance, by modeling the internet as a directed graph, as a by modeling the internet as a directed graph. Interestingly, I have a whole playlist on graph theory, so there you can understand better what directed graphs are. So you can check out the playlist on uh, graph and network theory. So internet as a directed graph, right? So each web page, each web page is a node and a hyperlink from one page to another represents a directed edge. Okay, this is the principle on which Google runs. So if you are searching for something, the websites that come up, follow this kind of algorithms. So the importance of a web page is determined using eigenvalues and eigenvectors of a matrix representation, of a matrix representation, representation of the web graph. So, you can actually write every graph. One of the ways of representing a graph is in a matrix form. So matrix representation of the web graph. Okay. Specifically, PageRank, you can call it Google's PageRank, right? Google's PageRank finds the principal eigenvector of a stochastic matrix. And that is what we call it. That is the Google matrix in this situation. Okay, to find the principal eigenvector of the stochastic matrix or the Google matrix to assign steady state probabilities to web pages. Okay, so that's the idea. So that is how pages are literally ranked. So can we look at an example? So consider a simple web of 3 pages with the following links. Okay, so you have, let's say you have page A, B, and C, and then they have links on those pages. You have links to, so from A, you have link to B and C. From B, you have link to C. From C, you have link to A. So just as simple as this. So from A, you can navigate to B or C. From B, you can navigate to C. From C, you can navigate to A. So that's what we have there. Now, you will see that we represent, so we represent this using a column stochastic matrix L. Is a column stochastic matrix L, where each entry Lij is the probability of jumping, from page J to page I. Okay, so now that L is given as this 0, 0, 1, 0, 0, 1, and then half 0, 0, and then half 1, 0. Okay, so that's what we have here. So you discover that each column sums to 1. Okay, each column has to sum to 1. Each column sums to 1, ensuring it is a stochastic matrix. So as you can see, 0 plus half is 1. 0 plus 0 plus 1 is 1. 1 plus 0 plus 0 is 1. Okay, so you have 1, 1, 1 like that. That's ensuring that it is a stochastic matrix. Now, with that in place, right? Okay, I mean, that's step 1 so far. Step 1 for the worked example is, where you're constructing the link matrix. Okay, so that's like step 1. So constructing the link matrix, that's what we've done so far. And that is what we ended up constructing right here. Okay, so if we go for step 2, in step 2 now, we want to compute the page rank. Step 2, so computing the page rank vector. Okay, so here we actually seek a steady state. We seek a steady state probability vector P, a steady state probability vector P, such that LP is equal to P, So here, this means P is an eigenvector. P is an eigenvector of L corresponding to eigenvalue lambda equals 1. Okay, that has to be guaranteed. So let's go ahead to solve. So now solving 0, 0, 1, half 0, 0, and half 1, 0 by x, y, x, x, y, z equals x, y, z. Okay, so this is what we have here. Now, this is more like our LP equals P. That's exactly what's happening here. So if you try to solve this now, just like I like to do, I have a simple way of working this out, right? For instance, we have just one column of this, so we write it once, and then we have 3 rows of this, so sorry, we have one column of this, so we just write it in one column 3 times. Okay, so we have x, y, z, x, y, z, and x, y, z, so that we now go for the first one, 0, 0, 1, like this. So this is 0, 0, 1. So it means x times 0, y times 0, z times 1. Then next we have half 0, 0 this way. So it means we have half 0, 0. That's x times half, y times 0, z times 0. And lastly, we have half 1, 0. So that means we have half 1, 0 here. So all of this now is equal to x, y, z, like we have on the right-hand side. So if we tidy all of this up, so x times 0 is 0. So this is gone, this is gone. So we just have z, and z now is equal to x, because this is this to this, and this to this. So that is x, z equals x. So that's established. Then the next thing is that so y times 0 is gone, z times 0 is gone. So we have half x. So half x now is equal to y. Okay, half x equals y. So I mean, that's also something, right? Y, that implies that y is equal to half of x. Okay, so that's gone. So we can also have the last one, which tells us that half x plus y equals z. Okay, half x plus y equals z. Okay, so, well, we can number this equation, so we can refer to them 1, 2, and 3. 1, 2, 3. So, I mean, half x plus y equals z. And then we already know we can put everything together as x, right? Substituting, so we can easily substituting 1 and 2, substituting 1 and 2 in 3. In 3, what happens? We have half x. You know that y is half x also, so we have half x again. And you know z is equal to x also from 1. That's x. So what happens? This is half x plus half x. That's simply x. Interesting. So x is equal to x. That's not so, that it's not really interesting, right? It doesn't tell us anything. Of course, x is always x, which is always true, which is always true. Okay. So if we setting x plus y plus z equals 1, that is actually probability sum, right? That's probability sum. Of course, I have a whole playlist on probability. You want to check that out. So if you are dealing with probability, everything sums up to 1. So we now get, if we do that, we get that x plus half x plus x is equal to 1. Uh, okay. Now, I want to really make that clear enough. So let's not jump. So we know x plus y plus z equals 1, right? So we know we already, if we want to take everything in terms of x, so x is x, y is half x, That's what we got the other time. And we also got that Z is X, right? X is X, Y is half X, and Z is also X. So all of this should be 1, right? So we have X plus X, 2X plus half X. That's 3 over 2. Is it 3 over 2? So this is 1 plus 1, 2. That's 2 and half X, right? So this is 2 and half X equals 1. That means 5 over 2X is equal to 1. If we multiply through by 2, we have 5X equals 2. So X alone is 2 over 5, okay? X is 2 over 5, settled. So the next thing is we can then get every other thing. X is 2 over 5. We know that Y is half X. So that means we have half into 2 over 5, and that is equal to 1 over 5, right? That's Y. So Y is simply 1 over 5. That also goes. Then we know Z. Z is equal to X. So that means Z is equal to 2 over 5 again. So Z is 2 over 5. And that also goes. So with all this now, we have our results. We can say, therefore, X is 2 over 5, Y is 1 over 5, and Z is 2 over 5. So if you add everything together, you still see you get 5 over 5, which is 1. So with this, we have our result. We can then say, thus, so with this now, thus, thus, the PageRank vector, the PageRank vector is P. And that P now is X 2 over 5, Y 1 over 5, and Z is also 2 over 5. Of course, in decimal, that's like 0 0.4, 0 0.2, and 0 0.4 again. So that's site A has a chance of 40% of being visited. Site B has a chance of okay, I can say that, right? So this tells us that site A has a chance of 40% of being visited. Site B has a chance of 20% of being visited. And site C has a chance of 40% of being visited. So A and C have the same kind of importance. So we can just give the meaning to this. So we said meaning. So we have P to be that, right? Meaning pages A and C are equally important. They are equally important. They are equally important. While page B, has the lowest rank. Page B has the lowest rank. Okay. So in conclusion, eigenvalues and eigenvectors help solve the steady state equation, LP equals P, so ensuring that the power iteration method, I mean, I've done a video on power iteration method, ensuring that the power iteration method converges to a dominant eigenvector, okay, this is important, a dominant eigenvector representing web page importance, Thus, this fundamental approach enables scalable web ranking. in search engines, in search engines. And that is, of course, the secret behind Google and other search engines. Okay, so with this, we've come to the end of this video. So I still have, I think, about 2 months ago. I think there should be one on image compression and another one on population growth. Okay, so if you have subscribed, thank you. If you have not subscribed, go ahead and subscribe right now. And if you have hit the notification bell also, so you can always get alerted anytime a new video is released. Then comment, let me know how helpful these videos are for you. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Also, let me know. Yeah, and also like and share so that more people can have access to this great content. Till I come your way again, keep enjoying maths. Bye.